All right, I want to welcome everyone here at the Wisconsin Energy Institute and welcome to those joining us online. My name is Scott Williams. I'm the Research and Education Coordinator of the Wisconsin Energy Institute and also the coordinator for the Sustainable Energy Seminar Series that we hold here at the Wisconsin Energy Institute every other week in the fall and the spring semesters. And our goal with the Sustainable Energy Seminar is to highlight the cutting edge research from across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop solutions. And throughout the series, we hear from folks in science and engineering, as well as social sciences and humanities, to learn about the different ways in which they view sustainable energy challenges and solutions. The seminar is open to the public, but it's also a course for students in the undergraduate Engineering for Energy Sustainability certificate, as well as the Master's in Sustainable Systems Engineering. And we are presenting this in a hybrid format, so you're welcome to join us in person here at the Wisconsin Energy Institute or online through Zoom webinar. For those joining through Zoom, live captioning is available. If you'd like to use that feature, just click on the Show Captions button. And if you have a question, please use the Q&A feature within Zoom webinar, and I'll pass the mic around here for those in the room. And our presenter today is okay stopping mid-presentation if there's any particular questions related to what he's talked about so far. And with that, I'll introduce our speaker, Sagar Rathod. Is an atmospheric and public policy scientist who studies air quality and climate impacts. He is currently a postdoctoral research associate in atmospheric and oceanic sciences here at UW-Madison, studying sulfate aerosol modeling and ocean heat modeling. He previously served as a postdoctoral research associate in public affairs here at UW, focused on air quality and health modeling, methane emissions, and integrated assessment modeling. He did his PhD in atmospheric science from Colorado State University on the topics of anthropogenic particulate metal emissions and their Earth system impacts. And so today's talk will focus on some of his past research related to side effects of decarbonation with a focus on metals and ammonia. Welcome.
So thank you, Scott. Welcome everyone, and thank you so much, Scott, for having me. Welcome everyone to attending online as well. Oh, nothing, it's just showing me that I was mute, but I am okay.
You're okay.
Awesome, sounds good. Yes, so today's talk will feature two examples of how, as society, we want to move from fossil fuel to renewable energy sources, that is from coal, oil, and gas to solar, wind, EVs, green shipping, and how in the transition from fossil fuel to renewable energy, there could be some environmental side effects that we should consider before fully deploying that or in the process of deploying that. Some of these are already happening, and the ammonia case is for a hypothetical 2050 scenario where we simulate what could happen when we fully replace the current shipping fuel with ammonia. So the talk is divided in two halves. The first half will talk about the metals, and the second half will talk about ammonia. And in both of them, I'll talk about the energy equity, not the energy, but the impacts equity aspects and the impacts aspects. So, but first, thank you so much for being here. And mid-presentation questions are super welcome. So as Scott said, I'm happy to pause the presentation, take questions, and answer any clarifying questions. But if you have a longer question, we can take it in the end. But any clarifying questions are super welcome mid-presentation as well. The purpose of this talk here at the Energy Institute is to highlight two cases in which air quality impact or air quality side effects of energy transition could be non-trivial. So when I say environmental impacts, I'm focusing on air quality impacts. There could be a lot of other impacts such as water and land and social impacts, but this talk particularly focuses on air quality impacts. And when I say side effects, they can be unintentional but known, could be unknown too at some point. So the ammonia one is more on the unknown side, but the metals one is known side, that those impacts are currently happening. They're unintentional, that is, we want to move from fossil to renewable, but they're happening because the production process and the other the deployment processes just include those processes that cause environmental impacts or air quality impacts. So the general idea here is that we want to move from fossil fuel to renewable energy sources. And while decarbonization creates new opportunities, that is, we can now sustainably source materials. Now we can rely on sources that can give us continuous and energy at a very low carbon cost. However, it also creates new problems. So in this talk, I will be playing devil's advocate at some level. That is, but in all of this talk, while I underscore that there could be impacts, I'm not saying that we should not transition. All I'm trying to say is that we should transition, but with caution. So the first case is of metals. And here the driving question is that how much air pollution is currently happening and can happen in the future to meet the metal demand from future solar, wind, and EV addition. And here the air pollution happens from mining of metals, and metals can be any metal like iron, aluminum, copper, the main metals, or could be the special metals such as vanadium, nickel, neodymium, and other rare earth metals or critical metals. The other process is smelting, which is the melting and the purifying process of metals, and after which we can use it for final steps. And before I even talk about the the concept, I'll just lay out the findings and the whole summary. That is, a faster decarbonization means that we'll purchase more and install more solar, wind, and EVs. That is, yes, we want to move from fossil to renewables. And if we buy more solar panels here, or anyone buys more solar panels, that means there will be more demand of metals as well. And that is the second point here. That is, as we add more renewable energy, that means we'll have more metal and mineral demand. Now, currently, mining and smelting, the two main aspects of metal requirement, fulfilling the metal demand, they contribute a high proportion of air pollution in many regions, particularly the ones near mining areas or the ones near industrial production areas. And in this work, we found that mining and smelting to meet the future renewable energy demand can lead to more particulate matter air pollution. For this study, I'm focusing on particulate matter, which is tiny, tiny smoke-like particles, very small, fraction of the diameter of human hair, that can go deeper in your lungs and cause health effects. So we found that yes, as we try to meet our metal demand, the mining and smelting can lead to more air pollution in some regions. So in this talk, I'll talk about what those regions are, what timing it could happen, and if we abate it, that is, if we control it, how much abatement can we get? And the general idea here is that we want that a rapid shift from currently fossil fuel dominated electricity mix. This is the global mix where a lot of energy comes from coal, oil, and gas, to a 1.5 degrees Celsius climate goal by 2050 or 2100, depending on the scenario. We'll need to add a lot of wind, that is blue, and solar, that is orange here. Now, the 1.5 degree climate goal is important to understand that we don't want to exceed 1.5 degrees Celsius compared to pre-industrial times. That is, we have to move to renewable energy sources by 2050 and by a lot to not exceed that 1.5 degree Celsius threshold. Now, metals form an integral part of the modern renewable energy systems. That is, we need these conventional metals such as iron, aluminum, and we also need some rare earth metals such as gallium or tin or indium and other ones. And that also depends on what kind of mix or what kind of energy source we are going for. That is, solar needs a different type of metal, wind needs a different type of metal mix, and EVs require a different type of metal mix, where EVs generally need more lithium, cobalt, and nickel for the batteries. However, wind, solar, and EVs are more metal intensive compared to the conventional or the fossil fuel energy sources, where on the y-axis here is the metal requirement just to set up a plant. So it's not the operating metal requirement is just to set up a nameplate capacity of a plant and tons per gigawatt. So if you set up a 1 gigawatt plant, a coal power plant somewhere here, it will probably need just a very little amount of metals, just the framework of the plant and all the pipelines that we need in the plant. However, to make a 1 gigawatt of solar plant or a wind plant, it needs an order of magnitude or even higher, or multiple orders of magnitude higher amount of metals. I'm not focusing on geothermal, nuclear, or hydro, even though these are clean, just because in the future, their role in the energy systems to reach 1.5 degrees Celsius is not as much as we saw in the previous graph. And these two will be the ones that will lead to the most demand. So for the general idea, we need more solar and wind. However, solar and wind are more metal intensive. So what happens when we mine and smelt them? And this is from the International Energy Agency study where they model that the annual demand of some of these metals could be about a factor of 40 than what we are mining and smelting right now. So if the world, say, is mining about a ton of lithium right now in 2050 or in the next 20, 30 years, so yeah, it's in 2040, will be mining or will be annually mining about 40 times more lithium just to meet the batteries and the EV demands. And the same, and this value is higher for all other metals as well. However, here is where the equity aspect comes in. That is, the regions that are producing these metals are not the regions that are processing these metals or assembling these metals, and they are not the same regions that are actually demanding these metals. So think of it this way, that countries like China, the regions in EU and the US, they are the major demanders, or they are the major purchasers of solar, wind, and EVs. However, they don't actually mine or smelt these metals. Only a small number of countries do, and those countries are often low and middle income countries. Now, the raw material that is mined here then goes to these countries. Depending on the metal, depending on the facilities these countries have, and depending on the supply chain efficiencies, these countries then smelt the metal and make it into almost a finished product that then goes to these countries for installation. So it causes an equity aspect to that. The countries that actually will install the solar panels will not get any of the mining and smelting impacts as the other countries do. And the other aspect here is that, as we see here, this is an example of 6 or 5 metals, but it is really geographically concentrated. That a metal like copper, only a few select countries have the mining reserves. So only so the mining impacts are also geographically concentrated. Now, most processing of copper to convert it into refined copper that can be used in wires and solar panels happens only a few other small countries. And then the countries that eventually make it, converted into the refined material are also different. And not only different, but they are a small number of countries. So these impacts could also be geographically concentrated. And this is based on the current production geographies. Now, these geographies can change in the future based on if a country identifies more reserves in the future, or if a country increases its production or processing capacities. But this study focuses on what if these geographies stay true in the future as well, or stay the same in the future as well. Now, this is the air pollution aspect of it, where I'm showing that the current levels of air pollution are higher from mining and smelting in different countries. This shows only in Santiago, Chile, a major, the capital of Chile, and a very big town, where copper mining and smelting, or mainly copper smelting, contributes about 15 to 20% of PM 2.5. Now, PM 2.5 is, as I said, is a fraction of human hair diameter, very small smoke-like particle that you, upon inhaling, can reach to deeper lung levels and cause health effects. So currently, some of these cities are experiencing about 15 to 20% of air pollution just from copper smelting. And what would happen? Say if Chile mines and smelts about 5x or 10x more copper in the next 20 years. Then these numbers, and if it goes unabated, that is, if it goes uncontrolled, then these numbers can, or the relative contribution to the air pollution in Chile could be higher as well in the future. And now this comes back to the driving question, that is, how much air pollution from mining and smelting of metals to meet the future solar, wind, and EV demand. And as I said, this is an example of a human hair, about 50 to 70 micrometer diameter, whereas particle matter is this tiny dot here, which is a small fraction of the diameter of the human hair. And to estimate basically how much air pollution can happen, we use two decarbonization scenarios. One is a business as usual, or called current energy policy, and another is a 2 Celsius goal or rapid decarbonization scenario to model the growth of solar, wind, and EVs. And we also looked around, we also modeled how we will model, or how we will actually process metals using different smelting technologies and different abatement measures. And the general idea is that, yes, currently all countries use dirty smelting processes, but in the future they may use cleaner production methods. So that is all modeled in this work. And this is a schematic of how we modeled it. So we use two scenarios, one with less renewables, one with more renewables. That is, a scenario with less renewables will have lesser metal requirement and overall lesser impacts, but then the timing and the locations of those impacts are different. The one with more renewable energy addition has a renewable energy addition higher from all the countries, and the timing is also different in different parts of the world. That line is a schematic. Those values are just for illustration. So any energy generation and technology production means that we'll basically add more of these. And the addition of these solar, wind, and EVs triggers a metal requirement. Now this metal requirement is met via various processes such as mining and smelting. And then these mining and smelting emit health and climate relevant air pollutants. I'm focusing on health relevant pollutant, but the climate relevant pollutants are sulfur dioxide that is emitted highly from nickel and aluminum mining and smelting. And, and all of these processes also emit some amount of carbon dioxide as well, which is a climate relevant gas and not an air pollutant here. And in terms of the results, they're more intuitive than we think, in that there is a small number of countries that bear most amount of air pollution. And here we first look at the left panel. The y-axis is year, the x-axis is the air pollution or the emissions in terms of gigagrams of PM2.5 from mining and smelting just to meet the metal demands. Different colors are different macro regions. Some of them are individual countries like China and India and Australia, New Zealand, or Russia, but some of them are macro regions such as North America and Asia. And first we look at the scenario in which we add less renewable energy, and we see that in the next 30 years, we might increase or almost double our emissions just from mining and smelting. However, if we add more renewable energy, that is in this more renewable scenario, we might from 200 to about 700, so almost triple or slightly more than triple our air pollution or air pollutant emissions from mining and smelting. Now, the countries that will bear this burden are also different. That, for example, India will have a larger share. China might also have a larger share. And this is based on how much currently India and China process these metals. Now, this does not take into account how much different countries, how much Africa might process more metals in the future. If, say, the mining and smelting ramps up in Africa in the future, then the African contribution might be higher and the contribution from India and China might be lower. Now, is there a solution here, or not solution, but how do we reduce these emissions? And we also modeled a case in which we employ or deploy more emissions control technologies to all of these countries. Some of these countries, such as North America and Europe, already have higher amount of emission control methods. However, we also modeled that what if we also make abatement possible for some of these currently low-income countries, and that is shown with the dashed black line here. That is, if we employ, we also, the modeling of these abatement technologies was also done at a reasonable timing. That is, we did not model that, okay, all the countries will have good abatement measures from tomorrow. We modeled it in a tapered way, that is, countries will gradually have that abatement measures. And we found that if we model that abatement, then we can reduce our emissions from about 200 currently to basically 0 in the next 30 years. That is, there are ways to cleanly produce these metals and lead to less emissions. And that also applies to even if we mine and smelt more renewables or more metals for more renewables, that is, we can get emissions to basically 10% of what it could be. But however, the employment of the application of these abatement methods is expensive. So we did not look at how countries could finance these abatement technologies. However, we showed that the application of these abatement can lead to lower pollution in different countries, even if they apply these abatement methods at a reasonably faster rate.
Can I ask a quick question?
Mhm.
What are some examples of the abatement technologies that you might use, and how much of it would be kind of retrofitting current plants versus building new, cleaner plants?
Yeah, no, that's a great question. In this work, so abatement technologies for particulate matter generally include bag filters or electrostatic precipitators or scrubbers in existing power plants. We did not model the presence of a new type of processing facility. That is, we only focus on retrofitting current processing, current smelting aluminum, say an aluminum smelting plant that in India, say, has a back filter, which is not as efficient. And we model what if that aluminum smelting plant in India has a back filter that is more efficient or uses a wet scrubber instead of a dry scrubber, and, and all that efficiency improvements on existing smelting plants.
Just an observation.
Mhm.
So for metals that are being produced, smelted and processed, unless there's, if there is competition between different countries in those areas, it's going to be very difficult to have anybody take the lead in abatement technologies, because those technologies that will immediately find themselves raising the price of feedstock and perhaps finished product.
Yes, no, that's a great observation. And that is how a lot of these countries are able to keep the prices low right now as well. And as we saw in the previous slide, that some of these countries, air pollution in even major cities, their capital cities, about 20% of it comes from the smelting industry, which is a large industry, say in Chile, and is a large industry in other countries as well. But yes, that's a great observation there. So even if the metal-related mining and smelting, just to meet the renewable energy demand, might seem higher, to put that into context, how much we are emitting currently from coal power plants, or how much basically PM2.5, so the smoke we are emitting from coal power plants, oil and gas power plants, is shown here for context, and how it can change as we rely more on renewable energy and less on fossil energy is also shown here. So in this plot, the left one is the less renewables plot, and the right one is the more renewables plot. So the current energy policy and rapid decarbonization shown at global levels. The y-axis here is the total PM2.5 emissions in gigograms per year. Now, the black color here is the total anthropogenic combustion, so all the smoke coming out from coal, oil, and gas power plants, including cars, including diesel trucks, and everything else. And the orange one here is mining and smelting only. So this top and on the bar, on the area plot. And this red dashed line here is the contribution from mining and smelting to total. So it's orange divided by orange plus black. And it's shown here on the right y-axis here. And the general idea of the finding here is that even if that number seemed big in the previous plot, compared to how much we are emitting right now, it's a very small amount. However, if we decarbonize slowly, we'll still emit a lot more from our current energy sources and diesel trucks at coal and oil and gas power plants. However, if we decarbonize fast in the next 30 years, will decrease the anthropogenic combustion part a lot quicker, leading to greater air quality benefits for all. However, our relative contribution, that is the red dashed line from mining and smelting, will be slightly higher, could be a lot higher depending on the region, and that is what I'll share in the next plot. But the general idea is that, yes, slower decarbonization has lower contribution from mining and smelting, but the overall, that is the sum of black and orange here, is higher than if we move in a faster decarbonization or a faster transition to renewable energy way. But the one key takeaway here is that faster decarbonization wins, that even if we have higher contribution from mining and smelting, our total is lower, and that's what leads to better, greater air quality benefits. And this is the final slide from the metals component, that the emissions burden is not equally distributed, and that's where the energy equity or the impacts equity comes in. And again, on the left panel is the less renewables or the slower decarbonization plot, and the right panel is the faster decarbonization scenario. Same color schemes. The y-axis in both these plots show the total anthropogenic combustion, the total PM 2.5 emissions, and the red dashed line shows the contribution from mining to total, segregated by regions. Some are individual countries and some are macro regions. And what I want you to focus is on two things. One is the absolute amount, that is the total sum of orange and black, and the red line here, that is the relative contribution of mining in India and North America and EU, just two countries for now. And then we can look at other countries as well. That countries such as richer countries such as North America and EU, the relative contribution of mining and smelting is basically zero. That is, these countries currently don't mine and smelt a lot of metals. So their impacts are going to be less too. And they will also benefit the reduction in overall emissions due to decarbonization. That is, everyone is decarbonizing, but these countries will decarbonize and not get these impacts. However, a country like India or China, where they will also get the benefits of decarbonization because they will also add more solar panels, more wind turbines, and EVs. However, they might get more impacts of mining and smelting because these are the countries that are currently mining and smelting a lot. And so that causes us inequitable impacts. That is, while everyone gets the overall benefits, some countries might get the side effects from mining and smelting of these metals. And those side effects may be about the contribution from mining and smelting may reach about 10 to 15% in some countries such as India and China, but may just reach about a couple of percents in some high-income countries. So that was the metals part, and now I'll quickly go to the ammonia for shipping component, for shipping sector. Here the story is that the shipping sector, that is the international shipping sector, currently emits about 2 to 3% of global anthropogenic carbon dioxide, and it causes about 80,000 or even more than 100,000 in some studies premature mortalities due to air pollution. So when these ships move, they consume diesel and heavy fuel oil, and when they burn that fuel oil near ports, and not only near ports but in remote ocean, that smoke travels to populated areas sometimes and leads to health effects, and it causes about 80,000 premature mortalities due to air pollution annually globally. Now, modeling groups, and by modeling groups, I mean the energy modeling groups that use a combination of energy, economics, the feasibility of how different energy systems can use fuels. They predict and they project ammonia can be a future dominant shipping fuel. that is currently ships use heavy fuel oil, but in the future they can use ammonia. They have to use ammonia to meet the climate goals, that is. Now, ammonia emissions have come with their own side effect, which is highlighted here. That is, when you burn them or just you emit ammonia, it contributes to secondary particulate matter formation by reacting with sulfates and nitrates in the air. And this is more of the atmospheric chemistry component, where if you have ammonia in the air, it quickly reacts with existing other pollutants in the air to make particulate matter that when you inhale, it can also cause health effects. While inhaling ammonia by itself also causes health effects, it also reacts with other chemicals to make particulate matter that can have its own side effects there. And this study that narrows down the geographical scope from global to just the port of Singapore, and the port of Singapore currently sells about 20% of the global total shipping fuel. And in this study, we estimated the air pollution that can happen from ammonia leaks, from storage and bunkering at the Singapore port, assuming that it will continue selling 20% of the global shipping energy in the future. And we found that PM2.5, that is the added particulate matter due to ammonia leaks, over Singapore could increase by 20 to 70% compared to a cleaner baseline. And it can lead to about 60 to 200% higher premature mortalities in a future 2050 year. And the background of this study is that international shipping currently consumes heavy fuel oil. And as we can see in this plot from Zhang et al., that mainly near port cities in the US, Europe, and elsewhere, even in China and India, it causes about 80,000 premature mortalities per year just due to PM2.5 air pollution. And on top of that, it emits about 2 to 3% of global anthropogenic carbon dioxide. Now, the shipping fuel operations, that is, when a ship, say, goes from Beijing to, say, it is going to Europe, it will make its journey from Beijing to, not Beijing, sorry, Shanghai to for Singapore, maybe get some refueling, then maybe go to Mumbai, and then go to Suez Canal, and then it make its way to Europe. And across all of this journey, they've all these big ships that contains those containers and cargo. They stop for fueling and refueling all the time. And the ship fueling operations are very concentrated. About a small number of ports basically control all the ships fueling and refueling operations, and that the port of Singapore sells about 20% of global shipping energy right now. And Singapore does not itself drill that oil or shipping oil. It basically buys that from some other countries and then sells it at its port. And to put this into perspective, imagine this quick trip on University Avenue that sells, and imagine that it sells about 20% of all the gasoline sold in Madison, Sun Prairie, Fitchburg, Verona, and a few other areas. And imagine the line that could be there. That is, imagine a small region selling a lot of gasoline, or about 20% of the gasoline sold in all of these areas. And then imagine that if we move that, if instead of selling gasoline, this port or this gas station will sell ammonia in the future. That is, they will have to not only change their infrastructure, but also imagine that this gas station will have to have big ammonia storage tanks and big ammonia infrastructure, and that all the cars that will come will also carry ammonia here. As I said, that energy modeling groups predict ammonia to be a leading maritime fuel in the future, and we can look at the left plot here. That is, currently all the ammonia that is produced, about 200 million tons, is used for existing uses here, which is basically for fertilizer use. However, in 2050, to meet climate goals, shipping industries will also have to cut down the carbon dioxide emissions. And these modeling groups predict that the ammonia demand will almost double just to meet the shipping demand. So while we want to move from heavy fuel oil to ammonia, and it's the same story as the metals, right? That is, we want to move from fossil to renewables, and it comes with its own side effects. And even in the shipping sector, we want to move from heavy fuel oil to ammonia. However, ammonia comes with its own side effects. That is, ammonia is leaky. That is, if you store it in a container, it tends to leak out because it's so volatile. Now, the leaked ammonia, once it is out in the air, it mixes with other reactants such as sulfurs and nitrates to make secondary air pollution, and which, when we inhale, causes health effects. And then the hard aspect here is that ammonia's emissions are difficult to abate. That is, ammonia being a volatile gas, it is difficult to stop its leak. And also imagine that in a bunkering or in a big port like Singapore, where you have tons of ships coming in and out, it involves a lot of moving parts that ships come with and existing ammonia tanks. They're not coming right now. We are hypothesizing that in 2050, when we have moved to an ammonia economy for shipping sector, ships will come with ammonia tanks and will will have big ammonia storage on port, and will use nozzles to refuel those ships with ammonia. And all of that process, it may involve some leak. And this is what we are quantifying here, that even if it's a small amount of leak, what could be the air pollution from that, and what could be the health effects from that? So this is how it may look like in the future. And this is the reality for some of the ports right now that are selling ammonia. And the high-level question we are trying to answer is that what could be the ammonia emissions from storing and bunkering it in ports, and what could be its implication for air pollution? So in this study, we look at ammonia emissions from leaks, from if you store a lot of ammonia just at the port, and if you the ammonia leaks from the fueling operations alone. To do this, we first estimated how much ammonia Singapore will store, and using some energy equivalency. That is, if Singapore sells about 50 million tons of heavy fuel oil, then it may, then that heavy fuel oil has an energy amount, and we convert it to ammonia's energy amount using energy equivalency. Now, leak values are from current literature estimates, which is about 0.05% of stored ammonia. These leak estimates may change in the future if we have better ammonia storage and bunkering technologies. Now, we use both the total amount of ammonia stored at Singapore and the leak values, and we plugged in a reduced complexity air pollution model. That is, now we have total amount of ammonia that might emit in Singapore, or that might get emitted in Singapore, and we plug it in an air pollution model to estimate the air pollution and the health burden using some concentrated response curves. Now, these concentrated response curves, they are based on this idea that the change of air pollution from some amount, from a small amount to a high amount, or small value to high value, leads to a proportional change in response, health response. That is, and also depends on the age of the population. That is, younger population might not react as much to changes in air pollution, whereas older population may react strongly to changes in air pollution. And we model that using existing concentrated health response, concentration response curves. On the result side, this plot here shows that in the baseline, that is where there is no emissions from shipping, just from existing ammonia sources, agriculture and some other industrial ammonia sources emit about 25-30 kiloton or gigagrams per year in 2050. And this is all a snapshot of a 2050 Singapore. And we simulated two scenarios where we have medium leak and a high leak scenario. In the medium scenario, these emissions from refueling and storing ammonia at the port can basically more than double the total amount of ammonia emissions in Singapore. If it still sells about 20% of global shipping energy, that is. If we have higher leak, if we assume a higher leak amount or higher leak rate, then it may increase the total ammonia emissions in Singapore by a factor of 5 or more. Now, what does this have? Now that we have this additional ammonia in the air of Singapore, what implication does it have for air pollution there? And to do that, we apply those health response curves or concentration response curves in both the medium leak and base leak scenarios. And we compare it with the heavy fuel oil case. That is in 2050, if Singapore continues to sell heavy fuel oil, the particulate matter concentration will still be about 6 micrograms. However, due to the added ammonia, it can reach to about 7 or 8 micrograms per meter cube just in the medium leak, and in the high leak, it almost can reach 10 micrograms per meter cube. So this is one of the cases where currently, just from selling heavy fuel oil in Singapore, its current air pollution is lower, but if it moves to a clean or a low carbon source such as ammonia, its own air pollution might increase by a bit, by about 2 micrograms per meter cube in a low leak scenario, about by 4 micrograms per meter cube in a high leak scenario. Now, for health effects, so this is the same plot as in the previous slide. It's a particulate matter concentration, and this shows the premature mortalities. That is in the 2050 Singapore, if it still sells heavy fuel oil, its health effects would be about 800, slightly less than 800 premature mortalities per year in the year 2050. However, if it sells ammonia instead, and so all the leaks from ammonia storage and bunkering, and then all the air pollution dynamics that can happen after that, it can increase the premature mortality in Singapore by about 300 in the medium leak, and by almost about 400 in the high leak scenario per year. Now, the finding here is that even if, and it's the same finding as the metals case, right? That is, when the whole world wants to move from fossil fuel to renewables, only some countries actually contribute to that movement. And a country like Singapore that is currently selling 20% of the total diesel or the total heavy fuel oil, if it moves to selling 20% of the global ammonia, then it will bear the burdens of from the ammonia leaks. However, globally, it will lead to total benefits. That is, in Singapore, it may lead to about 400 more deaths, but globally, just because we have moved from heavy fuel oil, we are avoiding about 16,000 deaths. So it again is a question of this inequity that in the whole global movement from fossil to renewable, some countries will experience higher air pollution and higher health effects, whereas globally it is advantageous for everyone else. And some of the global context is that the Port of Singapore currently is funding some pilot safety and feasibility studies, and they have funded a few shipping companies to study how they will store and bunker ammonia in some of their ports. And the context for the US is that the US has a few large ports here. That is the US Gulf area, third largest fueling and refueling port, and New York and LA are in the top 10 or top 12 ports in the world, just in the amount of selling the heavy fuel oil. And the US Department of DHS also has an ammonia port preparedness and emergency response, because storing a lot of ammonia in ports is also a safety concern. There are other laws or bills in the way that are pushing that are pushing the ammonia the ammonia usage in ports. And again, to summarize everything here, the general idea is that regional impacts could be non-trivial in a global energy transition. That is, a global energy transition favors the global population. However, regional impacts could be non-trivial, as we saw in the case of metals, where some countries, yes, globally moving faster, faster decarbonization is good in terms of reducing overall emissions, but the contribution of mining and smelting are different in different countries. Only some countries like India and China may get most of the burdens. And the same in Singapore, or the shipping case, where yes, the global movement from transition from heavy fuel oil to shipping avoids a lot of deaths, about 16,000 deaths. but it can increase about 400 to 600 deaths in the port of Singapore itself. And that's the idea here that I'm presenting that. And again, and I would like to reiterate that I'm not saying that we should not decarbonize. We should decarbonize, but with caution and in an equitable way, so that some countries don't get a disproportionately higher share or higher burden of some of these air pollution impacts. So, and with that, thank you.
Got a couple questions that came in online. So first question is, where did the data come to create these models and get the results?
Yeah, no, that's a good question. The first, for the metals, there were three types of data there. That is the energy addition component, that is how much energy we are adding in the future, and that comes from the International Energy Agency, that is the IEA's energy scenarios. And IEA is a big energy modeling / energy accounting nonprofit that models how we can move to renewable energy to avoid climate impacts. The mining and smelting technology data comes from collaborative work with an Austrian research group called IASA, International Institute of Applied Systems Analysis. And they have a model that basically predicts or simulates how different countries will use some of these technologies. That is, how different countries will use cleaner smelting in the future, and what will be the percentage of each in different countries. So, for shipping, the ammonia demand is calculated in this work itself by using energy equivalency and assuming that Singapore sells 20% of ammonia or 20% of shipping energy. That is, we first estimate the total amount of energy Singapore sells using heavy fuel oil, and then we convert it to ammonia. The leak factors come from current literature values that may not represent how technologies may advance in the next 30 years. So they could be considered slightly overestimating, and these estimates may be considered slightly overestimating. And the health response curves comes from internationally collaborative study called the Global Burden of Disease Study.
And another question is, do PM 2.5 emissions drift globally in the atmosphere, like from India to China, or to India to the US?
They do in a small regional scale. Some of these particulate matter, depending on how high they are in the air, can travel up to a few hundreds of kilometers, a few thousands of kilometers, depending on where they are, if they're getting washed out in the process, if the wind speeds are faster or not. But that transboundary pollution, or the transport happens generally between countries that are next to each other, and very less often different continents. So it's more of a country scale than a continent scale process. So.
Given the current, I guess, pollution profiles in India and China, could they, in fact, suffer the kinds of increases that you're showing? And would people still be able to live there? I mean, I know that it's easy to calculate these numbers, but actually then casting that on top of say a livability index or something like that, how does that look fare?
Yeah, no, that's a great question. And again, in this talk, I did not highlight that when I say India will have higher emissions, it's not all of India, but only the mining and smelting heavy regions inside India. So it may not actually happen near the big cities such as New Delhi or Mumbai, but may happen in mining towns, which may not have as many people there. So it again highlights another aspects of the inequity of impacts. That is, even in India, there could be disproportionately higher impacts in some regions than others. And those regions, yes, they may face higher pollution burden, and they may have to come up with abatement plans or personal exposure reduction plans. However, this may not represent what is actually happening or what may actually happen in all of India. So in short, there may be hotspots within the country itself.
So you didn't, and I don't know the distribution, the geographic distribution of say smelting within India and China, but this is what I'm sort of alluding to, that when this happens, there'll have to be some sort of relocation of the production facilities, I would think. To the extent that, for example, smelting is, I think you pointed out that smelting is not necessarily done in the same location where the mining is done. So I would imagine that smelting is often done, it might be done in Delhi and in certain parts of China where the industry is concentrated, and it will have to move from there in order to allow people to continue to live and work there, I would think.
Mm-hmm. Yes, it certainly can happen and it has happened in the past where industrial complexes have been moved or people have moved, and we did not model how that can happen, or how would people react to that, or how would industries react to that in the future. So.
This is important work, and I understand that the estimates get better as time goes on. How do you react to the possible politically charged impacts of the study, at least at this point? If I live in Singapore, I may or may not be comfortable with 600 people dying sooner compared to 16,000 not dying, period, due to this. I realize there's no good answer, but what do you think?
Yeah, it's this the not in my backyard aspect, or there are two aspects to it. That is, Singapore currently gains a lot from selling heavy fuel oil, so that their economy not depends, but it thrives on being a big port. So to be a big port in the future, and in the port of Singapore, as we saw, they are currently sponsoring pilot studies of ammonia shipping and bunkering, and they are giving tax rebates to the ships that are coming with ammonia tanks already on those ships. So they are incentivizing an ammonia transition, and I agree that the general population may not feel comfortable if that energy transition, even if it brings economic benefits, comes with environmental impacts. And that's why I think all those pilot studies and all those feasibility studies, they have that component of environmental safety as well. And I am not aware if the findings of those studies are out yet, but not many studies have been conducted to see if what could be the long-term impacts of storing ammonia at a port. And not only storing ammonia at a port, but storing ammonia at that scale at a port such as Singapore.
This may also come with significantly incremental employment in, for instance, Singapore, and income to change lives in a positive way. So I didn't mean to say that the news is all dour, but as this work is improved upon over time and other people cite it, fascinating to consider these options.
Yeah, no, that's a great observation. And energy transition, as I said in the first slide, it comes with new opportunities, but some problems too. And we should address those problems before we transition to those systems.
Yeah, I think along the same lines, Kermit Online asks, have you done any assessments of how to make the impacts more equitable? For instance, decentralizing Singapore from its position as a fueling center, but could that happen economically or politically?
That's a great question. And think of it this way. If you are a port that is incentivizing ships to come there to use the port to sell 20% of total shipping energy, but the shipping energy part is a small part. The other part is that ships use that port to unload and load cargo there. So all of that, it creates a flowing economy there. And would you let go of that big of a resource because some impacts can be detrimental to the local environment and people? And now this is in 2050, based on some of the current leak estimates. So I would assume that a big shipping hub like Singapore would probably invest more in making ammonia less leaky, improving that infrastructure than letting go its dominance as a global shipping hub.
Any other questions? I think along similar lines, how do we equitabilize the impacts of pollution without inequitably disrupting the economic viability of communities? How do we make the impacts more equitable without disrupting, the economics?
No, that's a great question as well. And that flows in the similar lines about climate impacts and the UNFCCC, where richer countries, they often pledge to donate, to support low and middle income countries in their transition to energy, cleaner energy, or to prepare themselves for climate adaptation and mitigation. And some of these problems can also follow a similar framework, where a country such as US or the regions in Europe that demand a lot of metal, renewable energy, and hence the metals, may support some of these low and middle income countries as they produce these metals. And the support could be to produce these metals in a more sustainable, environmentally sustainable way.
Any last questions? All right. Thank you again for your talk.
Awesome. Thank you. Thank you.
And that does it for this semester for the Sustainable Energy Seminar. So please join us again when the spring semester starts.